12 o'clock, so we'll go ahead and get started for today. You may or may not have noticed that I put up some test information yesterday. Is that visible enough? This is up on your Brightspace. I just opened this from Brightspace. The test is more or less going to look like it did last time. 4 questions, they're all worth points. You get 50 minutes. We'll write it next door in the lab again, just like we did last time. I'll give you a list of equations. I didn't post that yesterday because I'm not 100% done the test yet, so I want to wait till my formula sheet is finished before I post that. I recommend as you're reviewing, you start with the lectures, like everything we covered in class is fair game. The homework questions posted in class are good practice for you. The problem sessions are really good practice. Those are kind of test level. Assignments are also good, and then there's some old stuff also posted on Brightspace. If you get all that done and you're looking for more, the textbook has a pile of questions at the end of the chapter. It's hard to imagine you can get through all of that though. Please bring your ID. If you want to bring a sheet of notes in, that's fine. Single-sided only and handwritten. I think that's it. Only restriction on the calculator is it can't be a Wi-Fi enabled calculator. And I'll ask you to take off your smartwatches and put away your phones. Yeah, okay. And then for people who like, oh dear. People who like a list of topics to go through, I just scanned through the notes, and these are the topics we more or less covered since the last test. So we're going to focus on these topics. Of course, you can't completely forget about what came before because physics just builds on each other, but the bulk of it comes from this. It's just based on what we did before. Okay, questions? No, we're good. Okay. So last day, we did a lot of stuff last day. We finished up our section on capacitors, and we talked about energy storage in the electric field in between the plates of a capacitor. We started a new chapter. We talked about electric current, which is the flow of charge through a device. If charge is flowing, we know that charges are moving because current is moving charges. If it's moving, then it must feel the force. If there's a force, then there's an electric field. If there's an electric field, then there's a potential difference. This is why the charges are moving around. We defined current density as current divided by area, where area means the cross-sectional area of the conductor. Ohm's law says that current density is proportional to the electric field across the ends of the device. And then we defined conductivity and resistivity with which both describe how easy it is for current to flow through a material. Rho and sigma here, those are called material properties because they're constant for any particular type of material. We're going to start today talking about resistance, which is a device property. So it's related to these two things, but it is also specific to a device. Okay, so rho and sigma talk about the ease of flow of current through a material. We're now going to define resistance, which I assume you're more or less familiar with from high school. And it's going to be the ease of flow of current through a specific device. So resistance will be specific to a particular hunk of copper or a particular hunk of aluminum, okay? And it will be different for different pieces of it. Resistance has a symbol almost exclusively of a capital R. It has units of ohms, which has got a symbol of a capital omega. 1 ohm is 1 volt divided by 1 amp. I don't know why I wrote meters in my notes, but it is amps. Okay, we're good to hear? Let's think about what we talked about last day. We said that current density J was the conductivity sigma times the electric field. So this was the version of Ohm's law that we talked about yesterday. Let's think about these two bits of information. So we said that sigma was 1 over the resistivity. So current density is 1 over resistivity times field. That means that our electric field vector is the resistivity times the current density vector. In terms of magnitudes, the magnitude of the electric field is the resistivity times the magnitude of the current density. Okay, so there's our relationship with the magnitudes. Let's put electric field in context of potential. Electric field is potential difference divided by a distance. So if we have a specific device with a length L, so that's like this wire that we have right here, the electric field across the ends would be the potential difference divided by the length. So our electric field is potential divided by length. That's equal to rho. The magnitude of current density from our definition yesterday is current divided by area. And area means the cross-sectional area of a face of the conductor. So a little slice of a circle for a wire shape, for a cylindrical conductor, for example. Okay, let's rearrange this equation a little bit. So this means that V is equal to resistivity rho times our length L divided by our area A times our current. So I just rearranged this. So this tells us that the potential difference across two ends of a conductor is proportional to the current through the conductor. Potential is proportional to current. This constant of proportionality, this is the resistance R. So this brings us to the more familiar form of Ohm's law, the one you probably remember from high school, V equals IR. So this is also Ohm's law. It's just another way to express it, okay? So both are valid expressions of Ohm's law, just two different things we're looking at. So our definition of resistance then is the resistivity times the length of a conductor divided by the cross-sectional area of a face. We see that our resistance depends on what material it is. That dependence comes in through the resistivity, depends on how long it is, and depends on what the area is. So let's just write that equation down here and put that in a box. We said this was Ohm's law, so this applies the same things we were talking about yesterday. This is true for some materials, but not all materials. This applies to what we call ohmic materials, and in general, those are conductors. This doesn't apply to things like semiconductors or LEDs or diodes, things like this. So just a class of material, which is typically most conductors. Okay, are we good to hear? Okay, let's do an example or two. So in our example, I tried to work in a little bit of lingo. An 18 gauge copper wire has a cross-sectional area given. It carries a current of 1.67 amps. Let's find the electric field in the wire, the potential difference across a 50-meter length, and what is the resistance of that 50-meter length. So 18 gauge is just a little bit of lingo that tells us about the area of the wire. So if something is 18 gauge or a different kind of gauge, what you do is you look that up in a table and it tells you what the area is. So if you went to Radio Shack or Princess Auto and you asked for a certain gauge of wire, they would just reel it off the spool and you would get a specific size. That's what the gauge means. I typed in the problem what the cross-sectional area was. You could also just take that from the table. Either is fine. So let's make a list of the things that we know. The area of the wire is 8.20 times 10 to the minus 7 meters squared. If this chart were given, probably notice that this is in millimeters squared, so you'd have to do a conversion to meters squared. So make sure you're comfortable with those conversions. The current running through the wire is 1.67 amps. We know that resistance R depends on the resistivity. We look that up in a table as well. So we're told that it's a copper wire. So we look in our table of resistivities and we see that copper has a resistivity of 1.72 times 10 to the minus 8 ohms times meters. So we'll put that in our list. So resistivity of copper. And the length is 50 meters. On a test, I would either give you the resistivity or I would give you the table. On an assignment, I would expect you to know that you could look this up, okay? That you could just look at the table in your book and figure out the resistivity. So if you had an assignment question that talked about a gold wire, you'd be expected to know that you could just look up that value for gold. Okay, let's get into the questions. Question 1, find the electric field, or question part A. Well, in terms of the things we're given here, we know that electric field depends on the resistivity times the current density. And we know current density is current divided by area. So this looks like a good equation to find the electric field in the wire. So we'll fill in the resistivity and the current, divide by the area. And we get for our net electric field in the wire 0.0350 newtons per coulomb or volts per meter. This stuff is pretty much just straight up plug and chug. There's not a lot of interesting things to ask. Part B, find the potential difference if the length of the wire is 50 meters. Well, we know potential difference, the magnitude of potential difference is the size of the field times the length. So the potential difference across the two ends is 1.75 volts. And then the last bit, calculate the resistance. Two ways we could go at the resistance here, two possibilities. We'd get the same answer regardless. Resistance, we could do rho times L divided by A. We know rho, L, and A. Or we could say that resistance is potential divided by current. Both of those things will work out to give the same answer. If we go potential divided by current, we have 1.75 volts divided by 1.67 amps to get 1.05 ohms. So two equivalent ways to find their dealer's choice of what you do. Questions? That stuff's really straightforward. Okay. So let's keep going. So we've defined resistance and resistors. We're going to talk a lot about circuits. So we talked some about circuits with capacitors. Our next chapter is circuits with resistors. So we're building the tools we need to talk about those circuits. So the next little bit we'll talk about will be details about batteries and wires and internal resistance. So we already talked about this a little bit. If we have a battery, we could label the terminals A and B. So the top could be A, the bottom could be B. we know that inside that battery, there's a chemical reaction that does work to move positive charges towards the positive terminal. That's how a battery operates. So positive charges are moved upwards towards the positive terminal. So if our positive charges move towards the positive terminal, it means the top terminal A is positive, the bottom terminal B is negative. We have a separation of charges that results in an electric field inside the battery. Okay, so the charges are moving around because of the chemical reaction, which creates an electric field. So the separation of charges creates an electric field. Oh, those arrows showed up, okay. So that electric field we can label as an E. What else do we have? If we have an electric field and the separation of charge, then there's a terminal difference between, there's a potential difference between the terminals of the battery. So between the positive terminal A and the negative terminal B, there is a potential difference that we can call VAB. And that's just a standard notation for potential difference between the two terminals of a battery. We often call it VAB. This VAB is the potential between these 2 points. So there's sort of 2 ways to look at that. It's the potential difference between here to here on the inside, or it's the potential difference from here to here on the outside. Both ways are valid ways to look at it. Okay, so just 2 sides of a coin there. Are we good to there? Yep.
So you said the positive charge is traveling towards the positive plate, right?
Yep.
So you said negative plates are attractive. So why is it traveling towards the negative plate?
So the positive charges move up here because of the chemical reaction inside the battery. Yeah, so it's all that chemicals inside that works there. Yeah, your chemistry profs can talk more about that stuff. This is the positive terminal, this is the negative. That makes this side the high potential. This end is the low potential. That also makes sense with our electric field. We know that points from high to low potential. Then our charge starts to flow around the circuit. That's our current. So charge flows through the wire, comes around here. So we have current flowing through the wire, goes all around the circuit. So I is the current inside the wire. So the next little bit of detail is that the potential difference between the terminals inside the battery, this is where we introduce the notation and the definition for EMF. So the potential inside a battery is traditionally, and we still call it EMF. So the potential inside the battery is called EMF, and it has a symbol of the Greek letter epsilon. Historically, EMF stood for electromotive force. The reason they called it an electromotive force is that they knew charges were moving around, and they described this EMF as a force moving the charges around. Through the work, we now know that that's not really an accurate description. A more accurate description is to talk about the potential inside the battery, not the force inside the battery. So EMF is a potential difference. It has units of volts. It is not a force, it's a potential. So we don't really say electromotive force anymore. We just say EMF. So that's more of a dumb thing these days. Okay, next bit. So the potential difference inside is the EMF epsilon. If we had a perfect battery, so an ideal battery, that would mean it had no resistance to current flow inside at all. So nothing inside would prevent it from moving, no resistance whatsoever. So if we had an ideal battery, there's no resistance to the flow of charge inside. In that case, the potential difference between the terminals would be equal to the EMF. Okay, so if there's no resistance inside, the potential difference between the terminals is just the potential difference of the battery. That feels like a really obvious statement, but we'll start with the obvious and then we'll make it more difficult. Okay, next, we know that the potential difference is equal to I times R, where R would be the resistance of the wire. So the potential difference across the wire is that potential VAB. There's current I through the wire. It has a resistance R. So the potential difference, VAB, would be equal to I times R. And this is for the ideal battery. I would say that for the majority of our problems, we are going to talk about ideal batteries. Okay, so most of the problems we look at will be this case. But we know that not all batteries are ideal. Everybody's had a battery go dead on them at some point. Phone battery maybe dies, your Duracells start to leak and get crusty. So over time, actual real batteries do develop a resistance to flow inside. That's when the batteries start to die. So real batteries have what we call an internal resistance. So inside those batteries, at some point, it gets difficult for the charge to flow. This internal resistance, we give a symbol of a lowercase r. So the internal resistance of a battery is a lowercase r. What that means is that now the potential difference supplied between the two terminals is a little bit smaller than the perfect amount. And it's smaller by the potential lost inside. Okay, so there's a potential loss due to the internal resistance. So the net potential supplied by a battery is a little bit smaller than the perfect amount because we lose some potential with the internal resistance. And that's still going to equal I times R, which is how we write the potential outside the battery. So there's the potential inside, there's the potential outside. Okay, we're good to hear? So an ideal battery, say you buy a fresh pack of 12-volt batteries, those batteries will supply 12 volts. You use them for a few months nonstop, next thing you know, they're not supplying 12 volts anymore, right? They're going to go down to 10, 8, and then eventually none at all. So something that's kind of interesting about this is, what if we hooked up to a circuit where this resistance was about 0 and this resistance was about 0? So what if we hooked up a perfect battery to a perfect wire? What would happen then? So if R and R are both about 0. So the potential epsilon minus IR is equal to I times R. Potential epsilon is I times R plus R. If both of those things are 0, then the current through that circuit would be the potential EMF of the battery divided by the sum of the resistances. So if you hooked up a battery that was perfect, had almost no internal resistance, so a brand new battery, you hook it up to a wire that's ideal, so it has a really small resistance. Look at what we get for the current. We get the EMF of the battery divided by a number that is about 0. So equals really big. What happens, and we're getting handy to infinity as those resistances get really small, this is where stuff literally explodes and catches on fire. This is called a short circuit. So if you're doing circuit things, and you connect two wires with no resistance between them, you're going to get this short circuit and you're going to get this huge boost in current, which is when things get really hot and potentially catch fire. So you've got to watch out for short circuits. Yep.
Why do we need internal resistance for the battery?
Because sometimes they have internal resistance, right? Sometimes the chemical reactions slow down as the batteries get old, And they just don't work as efficiently because the internal resistance builds.
Okay.
Yeah, real devices just tend to
So
not
it's
be
just like a
perfect.
boost for the internal reaction.
Yeah,
So we use the resistance for the internal reaction to boost it up,
Yeah,
so that the battery lasts longer, something like that.
no, internal resistance is a descriptor of what happens as batteries start to die, right? So we use this to describe it, right? This is what physically happens to it. The reaction doesn't work as well anymore, and the resistance builds. So now we need to think about the battery with resistance, because that's just true. Yeah. Okay. Yep.
I just wanted to clarify that if R and R are exactly 0,
Yeah.
exactly.
If they were exactly 0, this would be infinity. Yeah. Which of course never happens, right?
Yeah.
We never get to infinity. That's too big. But currents can get really big, right? But, you know, this is why cars catch on fire, right? Because you get a short circuit in there somewhere. Okay, so next little pit stop on our discussion to bring us towards circuits is just a picture of some of the things we're going to see in our circuit diagrams. So when we draw circuit diagrams, we already introduced the straight line means an ideal wire. We say that this has negligible resistance or no resistance. So we'll have perfect wires in our circuits. This symbol is probably familiar to people who did high school physics. The squiggle is the resistance R. Batteries most often now are going to be labeled with an epsilon for the potential. So we're going to use that more often than V. If a battery has an internal resistance, the entire thing will be shaded yellow, and the internal resistance will be close to the battery. So that's your clue that this is an internal resistance. Hopefully we're going to get to talk about voltmeters and ammeters. Those are ways that we measure potentials and currents. And to keep our diagram complete, we also had capacitors. This is just a table I grabbed out of your book, so we'll be building diagrams with these symbols. Yep.
Does the short circuit also cause a voltage drop in the battery?
So when we get the short circuit, yeah, that'll do something to the battery for sure. Yeah, I guess this is where the battery catches on fire.
Yeah.
Yeah, because the current is getting so big, the charges are going to start to move faster and faster. The batteries can catch on fire. Okay, so next, let's just look at a circuit with and without an internal resistance and see what the difference is. So in our first circuit, and this is going to be a preview of the circuit analysis that we're going to do in our next chapter, let's find the current in each circuit and the potential across the resistor, the external resistor R. If the potential of the battery is 1.5 volts, this resistance is 50 ohms, and the internal resistance in this circuit is 2.5 ohms. So let's start with this circuit. This is a resistance of 50 ohms. The EMF of the battery is 1.50 volts. So the potential difference between points A and B, VAB, is equal to the potential difference of the battery, and is also equal to the current times the resistance R through Ohm's law. So then our current is going to be the potential difference divided by the resistance, 1.5 volts, divided by 50 ohms. So the current through this circuit is 0.030 amps, or 30 milliamps, either way. Find the potential across the resistor. The potential across the resistor is the potential AB, and we already said that that was 1.50 volts. Questions? Okay. For our next circuit, this one is still 50 ohms. Our little internal resistance is 2.5 ohms, and the EMF of the battery is 1.50 volts. What we said on our last slide, that the potential difference between points A and B is less than the potential of the battery by the amount equal to the potential lost across the internal resistance, IR. And that's also equal to the current through the circuit times the external resistance. So from this expression, we can solve for our I. Epsilon is I inside of R plus R. I is equal to epsilon divided by R plus R. So our 1.50 volts divided by 2.5 ohms plus 50 ohms. This time our current is 0.0286 amps. So when the battery has an appreciable internal resistance, the current through the circuit gets smaller. So we start to get a smaller current. The potential difference across points A and B then is either equal to IR or epsilon minus IR. Either will give the same answer. So the potential across points A and B is 1.43 volts. So when we have the internal resistance, we supply less potential to the circuit. Less is available because some is being dropped over the internal resistance. Okay, questions? So last day we mentioned power briefly as energy divided by time. Today we're going to talk about power in terms of circuits. So we'll use the same definition of power, but we'll apply it to a circuit analysis. So the definition of power is that it's the change in energy divided by the change in time. Power is delta E divided by delta T. Or it's the derivative of the energy with respect to time. So it's change in energy divided by change in time. It's the rate at which energy is delivered or the rate at which energy is dissipated. Symbol for power is P, units is watts, capital W, after a Scottish inventor, James Watts, from around the 1800s. So if power is change in energy over time, and the change in energy would be the work done, because energy is changed when work is done. And work done in an electrical circuit is charge times potential difference. So the work done would be the charge times the potential difference it travels through. Q over delta T is our current I. So when we think about the work done in a circuit, and we want to calculate the power, we see that power is current times potential difference. Pretty often we drop the delta and we say P is equal to I times V. For a very easy homework example, we can find two alternate expressions for power. So if we sub in V equals IR here, we can get one new expression. If we sub in I equals V over R, we can get another new expression. Okay, so a very easy homework example to do here. Questions here? Okay, so let's look at power in a circuit. So let's take our picture from the last time with our current we had last time, and let's find the power supplied by the battery. So we've got this battery, it's got a potential epsilon, that's 1.50 volts. We've got a current flowing through that's 30 milliamps. We want to find the power through the resistance, the resistor R. You know that power is current times potential. You know that potential is I times R equals I squared times R. So the power dissipated by the resistor is the current squared times the resistance, 50 ohms, to give us 0.0450 watts. Okay. So if you know the current and the potential and or the resistance, you can find the power in any circuit element. Okay, questions about any of this stuff? Okay, I figure most of this stuff was a recap from high school, but now we're all up to speed and we're ready to start chapter 26, which is our direct current circuits. What we'll get going with in that chapter is first we'll talk about resistors and circuits. We'll do resistors in series, resistors in parallel, and then combination circuits. Then we'll talk about circuits with resistors and capacitors together, RC circuits, and those are kind of interesting. So, we've already introduced our definitions of series and parallel connections. We're going to keep going with those definitions, but we're going to apply them to resistors now instead of the capacitors that we did previously. So, resistors in series, remember that means they're all connected in a row. So in this picture, I've got 3 resistors. So we've got a battery here. We know that charge is going to flow out through the battery. Why don't we even put that on our picture? As the charge flows, we know that that flowing charge is current. Current comes through, it goes through this resistor, then it goes through this one, then it goes through this one, and then back all the way around the circuit. So when we look at resistors connected in series, they all have to have the same current flowing through them because there's nowhere else for the current to go. Okay, so that same current has to go through. The battery supplies a potential delta V. That total potential has to be supplied over the 3 resistors. So this potential is split over the 3 resistors in the circuit. So they all have the same current, and the net potential difference is divided. Oh, I missed one key step. I'm very sorry. Back up to here. This is the cutoff point for the test. Okay, so everything we did to right here up to the end of chapter 5, here's the cutoff for the test. Sorry, I meant to mention this when we were there and I just slipped my mind. Okay, so then as we're starting the resistors, those circuits are not going to be on the next test. They'll show up on the final exam. Okay, so there's our cutoff for that test. Okay, back to this idea. So the potential difference supplied by the circuit is divided over the 3 resistors in the circuit. That means delta V, that net potential, is the potential across resistor 1, delta V1, plus the potential across resistor 2, delta V2, plus the potential across resistor 3, delta V3. That's a conservation of energy thing. The energy put out by the battery is used up in the circuit by the resistors. So let's use Ohm's law to write down what is delta V1, delta V2, and delta V3. So from Ohm's law, we know that potential difference is current times resistance. The current through resistor 1 is I. Multiply that by R1 to get delta V1. IR2 is delta V2, and IR3 is delta V3. So here's our expression for the net potential supplied by the circuit. Are we good to here? We did a similar sort of thing with the capacitors. So like we did with the capacitors, we said we could hollow out the three capacitors and put in one single equivalent capacitance that gave the same effect in the circuit. We can do the same thing with resistors. We can hollow out these three resistors. We can put in a single resistor called the equivalent resistance. And that's how we create an equivalent circuit. And this equivalent circuit, when it's connected to the same battery, will produce the same current I. So same current I when connected to the same battery with potential delta V. So our Ohm's law applied to this circuit says delta V is equal to I times the equivalent resistance. So we can take this, pop it in over here, and see what we get. So our potential is current I times our equivalent resistance. We see that we have current I in each of these four terms. So we divide both sides by I. And our result is that R equivalent equals R1 plus R2 plus R3. And if we had more resistors, we would keep going. So this is how we find equivalent resistance for a set of resistors connected in series. If you're thinking back to what we did for our capacitor circuits, this is what the equation looked like for capacitors in parallel. So make sure you don't get the ways you add them confused. So you got to remember which is which between your resistors and your capacitors. Because that would be one of the things I wouldn't tell you in a test, which equation to use. Okay, questions to here? Okay, so let's do an example. So in our example, we've got three resistors, 15 ohms, 4 ohms, and 8 ohms. So we can call them R1, R2, and R3. We're asked to find what is the equivalent resistance, what is the current through each resistor, and what is the potential across each resistor. So to find our equivalent resistance, we start by drawing the equivalent circuit. So I'll draw that beneath here. In my equivalent circuit, I've got my battery with my potential of 9 volts. I've got my equivalent resistance, which I label REQ. I've got my set of resistors in series. I know to get the equivalent resistance, I just have to add them up. So part A, REQ is the first resistance plus the second plus the third. 15 ohms plus 4 ohms plus 8 ohms to give us 27 ohms. Okay, so when they're in series, just add them straight up. Okay, part B, what is the current through each resistance, through each resistor? So let's think about what happens. If we look at our equivalent circuit, we know that we get current I flowing through this circuit. We know that that's the same current that flows through this circuit because that's our definition for an equivalent circuit for a set of resistors connected in series. They have the same current. I can analyze either of these circuits. This one is the easier one to analyze. I know the potential, the equivalent resistance, so I can use Ohm's law to find the current I. So Ohm's law, the equation we typically see, V equals IR. In terms of this problem, potential is current times R equivalent. Current is the potential divided by R equivalent. Potential is 9 volts divided by 27 ohms, 0.333 amps. So that's the current flowing through this circuit, which means that is the same current flowing through this circuit. So that is the same current flowing through each of those three resistors. Good there. Okay, next part C, find the potential across each resistor. We'll come back to Ohm's law again. We know that potential difference is current times resistance. We know each of the currents, we know each of the resistances, so we can find each of those potentials. So the potential difference across the first resistor is the current through the first one times the resistance of the first one. Equals 5 volts. The potential difference across the second one is current times its resistance. And the potential difference across the third one is current times its resistance. .67 volts. If you added these three things up, you would see that they summed up to be 9 volts because all of the potential difference needs to be supplied to the whole circuit. Okay, questions there? Yeah?
In part C, can I use potential divider instead?
Can you use potential what?
Divider.
Potential divider. I don't know what that means.
Like for the first voltage R1, we can make 15 over 27 times 9.
You can. You'd have to justify why that's acceptable. Like if that were a test question, it'd be fine to do for an assignment. But if it were a test, you'd have to explain kind of what's your rationale for doing that and prove why that's true. Yeah. Okay, the next, any other questions? The next bit we're going to do is resistors in parallel. We've only got a few minutes left, and I said I'd cover a class for a friend. So we'll stop there. We don't have class on Monday because we're off for Remembrance Day. So we'll be in class on Wednesday and our test on Friday.